All right, let's get right into it. We're going to explore a pretty groundbreaking idea today, one that could totally reshape our cities and how we get our power. We're talking about turning the very walls around us into giant batteries. So, I want you to start with this question. Just think about it for a second. It sounds like something out of a sci-fi movie, right? But what if the actual structure of your home, the concrete and steel, could also store all the energy you need? And this image right here, this is what that future could look like. A building that doesn't just sit there, but actively soaks up solar energy and stores it in its own foundation and walls, ready to power everything from your lights to your car 24/7. Okay, so why is this so important? I mean, why do we even need this? Well, it all starts with a really fundamental challenge in our energy system. It really boils down to this number, 40%. That's the share of global energy that buildings consume. They are just massive energy hogs, which, makes them a huge part of the problem, but also maybe a huge part of the solution. And here's the other side of the coin. As we move towards renewables like solar, which is great, we hit a different kind of wall. Solar power is fantastic, but it's intermittent, right? The sun isn't always shining, so to make it reliable, we desperately need a way to store that energy for nighttime or, for a cloudy day. And the problem is, our current batteries just aren't really up to the task. Lithium-ion, our usual go-to, has some real issues. We're talking fire risks, they're expensive, and they take up a ton of space. What we really need, our dream solution, is the total opposite. Something super safe, cheap, and you guessed it, built right into the structure itself. Which brings us to this absolutely wild, mind-bending new technology, cement-based structural batteries. So a CSB is exactly what it sounds like. It's a material that does two jobs at the same time. It's strong enough to be a wall that holds up a building, but it's also engineered to work just like a battery, storing and releasing electricity. It's the ultimate multitasker. Now, this idea has been floating around for a while, but it always had this one fatal flaw. The connection point between the cement and the metal part, the anode, was just bad. This would lead to corrosion and the growth of these tiny, spiky metal bits called dendrites, which would basically short-circuit the battery and kill it. And whoa, take a look at this. This is what that failure looks like up close. That is a microscopic view of the zinc anode, and it is an absolute train wreck of corrosion and those spiky, performance-killing dendrites we just talked about. So, to solve this pretty nasty problem, researchers turned to a really surprising place for inspiration: the human body. Yeah, let's see how this insight led to an absolutely brilliant solution. The key idea here is something called biomimicry, basically learning from nature's designs. And the researchers put it perfectly. Our bones, with their really unique structure of alternating hard and soft layers, gave them the perfect blueprint to follow. And this, right here, this is that aha moment. On the left, you've got the natural structure of a bone. And on the right, that's the new cement electrolyte. And that resemblance is definitely not a coincidence. They literally copied nature's design. So here's how it actually works. You have these rigid layers of cement that provide all the strength, just like the hard part of a bone. Then you have these alternating soft layers made of a special hydrogel. This gel creates these perfect little highways for energy to flow, and it also forms this clean, super adhesive connection to the anode. So it's both strong and incredibly efficient. Okay, so the theory is beautiful, right? But the real question is, did it actually work when they tested it? Let's take a look at the data. And the results were, well, pretty dramatic. The new bone-inspired electrolyte ran stably for 600 hours straight. Just compare that to the older designs, which failed in a tiny fraction of that time. That is a massive, massive leap in longevity. And it's not just about the hours, it's about the cycles. How many times can you charge it and discharge it? This new design handled over 3,500 cycles, which proves it's exceptionally durable and ready for real-world use. And here is the visual proof. Remember that corroded, spiky anode from before? Now look at the image on the right. After all those cycles with the new electrolyte, the surface is perfectly smooth and uniform. The problem is just gone. So when you look at all the stats, the new material just wins across the board. It's strong enough to be a real structural component, it's highly conductive, and it totally suppresses all that dendrite growth and corrosion that plagued the earlier versions. This is so much more than just a cool lab experiment. The real-world implications of this breakthrough are just enormous. Check this out. Here's a real prototype powering an LED sign. And to prove just how tough it is, the researchers literally hit it with a hammer. And it didn't miss a beat, it just kept working. I mean, come on, this isn't just a battery. It's a legitimate building material. This chart really puts the potential into perspective for me. Simulations show that if you just integrated these battery walls into a typical home, they could supply an incredible 99% of that person's daily electricity needs, almost completely self-sufficient. And what about the climate impact? Well, a single 33-story high-rise built with this technology could save 208 tons of CO2 emissions every single year. Now just multiply that by all the buildings in a city. The numbers get absolutely staggering. Which brings us all the way back to that initial idea, but now on a much, much grander scale. This technology really offers a pathway to a future where our buildings aren't just shelters, but are living, breathing power plants. A future where our cities could one day truly power themselves.